So now let's look at a different amplifier configuration, our non-inverting amplifier. And so again, our goal here is going to be to find a general expression for the closed loop gain. So we want to find general expression for our closed loop voltage gain A sub C. And so notice there are a couple of subtle differences between this configuration and the one that we've looked at previously, our inverting amplifier. So now our input is connected to our non-inverting terminal, the positive terminal. Our inverting terminal is indirectly connected to ground, but other than that, the resistor configuration is the same. We still have this negative feedback via our resistor RF. And to aid in our analysis, I'm going to go ahead and define two currents. We're going to have a current I1 going through resistor R1 and a current I2 going through resistor RF. So in order to analyze this, let's, again, like we've done before, start with our ideal op-amp properties. So we know we have zero current into our input terminals of the ideal op-amp. So zero current into ideal op-amp. So let's come up here to our ideal op-amp and add what that looks like. So that means we're going to have zero current here, zero current here. So of course we can do a KCL at that node there, and we can see that I1 is going to equal I2. Okay, so now our second property of our ideal op-amp is that our differential input voltage, V sub D, which is the difference between the voltage at our inverting terminal and our non-inverting terminal, is going to be equal to 0. And that's for, again, our ideal op-amp. Just to be explicit, I'll go ahead and write that down. And so in this case, we have our non-inverting terminal is going to be at a potential of VI. So we see that here. And because there's no difference between these two terminals, we know that this inverting terminal is also going to be at potential VI. So inverting terminal at potential. So potential is just another way to say voltage of VI. And so we could come here and we could label this point here has a voltage V equals VI. Okay. So now we've used our two sort of fundamental properties of our ideal op-amp. So now let's do our basic circuit analysis techniques to figure out the relationship between VI and Vout. So first we can say that our I1, well, we have our VI, if we want to define this more explicitly with polarities, is positive here with respect to ground, so we have VI here, and our Vout is of course with respect to ground, and we don't really have ground at this middle point here anymore, so we can't draw that explicitly across RF any longer. So let's take this one step at a time here. So for our I1, we can define I1 as negative VI divided by R1. And so the reason we have that negative sign is again from passive sign convention. Because our I1 is going through a voltage rise in VI, we have to include that negative sign when using Ohm's law or any equation relating our voltage and current. So now let's look at an expression for our I2. So our I2 is going to be equal to, so over here on the left side of our resistor, do this in a highlighter, over here we have a potential of VI. Over here we have a potential of V0. So the potential across this resistor is just going to be the quantity of VI minus V0 with polarity as drawn below. So what we can say is that our I2 is equal to that voltage VI minus V0 divided by RF, our feedback resistor. And so of course in this case our current is going through a reference voltage drop, so we do not need to include the negative sign from our passive sign convention. So of course, like we've done with our other cases, we can just combine these three equations, and then we're going to solve for the relationship between VI and Vout. So just substituting, we have of course our VI over R1, negative VI over R1 is equal to I1. and our I2 was VI minus V0 over RF. So what we can do then is we can break apart that fraction. We can say this is VI divided by RF minus V0 over RF. We can then collect our VI terms on the same side and factor out the VI. So we have VI times 1 over RF plus 1 over R1, which is equal to V0 over RF. And so I'm just kind of moving around terms. I've kind of switched the side they were normally on, so we get rid of those negative signs as well. And so from here, we can easily separate the VI and the V0. So we can say that AC, our closed loop gain, is equal to the output voltage over our input voltage, which is just equal to 1 plus RF divided by R1. And so we basically get that I've multiplied through this RF over here on both sides, and that's where we get that 1 plus RF over R1 term. And then of course we take the V1 to, or the VI to the right hand side. So we can write this expression in terms of our closed loop voltage gain like we have here, or we could also write it in terms of our output and input voltages. We could say our output voltage is equal to 1 plus RF over R1 times VI times our input voltage. So either way you want to write it, both of these are of course saying the same thing, but this is the general expression for our non-inverting amplifier configuration. Okay, so a couple notes for this general expression as well. So first is that we have the output and our input have the same polarity. And so that's because, unlike with our inverting configuration, we do not have a negative sign in this equation here. So that means we have the same polarity in our output and the input. Again, like we saw for our inverting configuration though, we see that our closed loop gain A sub C is only depending on resistors that are external to the op amp. So only depends on external resistors. And so that's good for us because that means that we can design this amplifier to amplify however we want it to. Okay, so that's all for our non-inverting amplifier. We're going to look at a couple more configurations before looking at some more numerical examples.